manera virtual en el enlace de YouTube. Antes de iniciar con el ponente, tengo los siguientes anuncios. Primero, los invitamos a participar en el ciclo de seminarios del Departamento de Química, de los cuales en pantalla se observa el link de internet y también el correo electrónico. Los encargados del seminario pues, son la doctora Dafne Saraía Guzmán Hernández y su servidor, el doctor Víctor Manuel Trejos Montoya. También los invitamos a que hagan parte y que participen en el podcast del departamento, el cual está a cargo del doctor Ricardo Peralta, la doctora Lucero González, el doctor Alexander Pérez de la Luz, y también que nos hagan llegar sus comentarios y también una invitación abierta a que hagan parte de la Gaceta Tlecachil, de la cual son encargados el doctor Humberto Laguna, el doctor José Luis Pruns Córdoba y el doctor Gregorio Guzmán González. Y los enlaces, o más bien los correos electrónicos, los pueden encontrar en pantalla. También los invitamos a que nos sigan en nuestras redes. También estamos en YouTube. Tenemos un enlace en YouTube, tenemos un enlace en Facebook, en X, y nuestra página de química.x.1.mx y nuestro correo electrónico. También agradecemos a nuestro patrocinador oficial, Estudios Farmacoeconómicos S.A.D.C.B., que hoy nos acompañan. Y bueno, el día de hoy tenemos al doctor Laszlo Puszlai, y que nos va a hablar un poco de teoría de líquidos. En este momento voy a hacer el switch porque necesitamos que la plática sea en inglés, entonces voy a hacer el switch. Ok. Primero vamos a pasar con un anuncio con el doctor Jorge Garza, ¿vale?
Muchas gracias, Víctor. Bueno, bienvenidas a todas y a todos a este ciclo de seminarios. Formalmente es el primer seminario del Departamento de Química, aunque tuvimos al inicio del año, pues, empezando el año, un webinar organizado por el área académica de Química Analítica, donde estaba al frente la doctora Dafne Guzmán y el doctor Jorge Juárez. Después vino otro seminario de teoría de la información, donde que está organizado por el área académica de química cuántica. En este momento ya empezamos formalmente el ciclo de seminarios dentro de nuestro departamento de química. No va a ser muy largo, estamos esperando 4 seminarios, colegas, 4 o 5 seminarios. No queremos abrumar con tanta información y que nos puedan acompañar, ya sea aquí en el Salón de Seminarios R206 o a través de nuestro canal de YouTube. Entonces, pues muchas gracias. Le vuelvo a agradecer a la doctora Dafne Guzmán por este esfuerzo. No la ven, pero está en los controles. Y al doctor Víctor Manuel Trejos también, que nos están ayudando con la parte del seminario. Muchas gracias. Adelante, Víctor.
Ok, entonces voy a hacer el switch para que podamos continuar con el seminario en inglés, ¿vale? So, okay. I'm going to talk about Dr. Laszlo Puszlai. So I'm going to share a short curriculum vitae of Professor Laszlo Puszlai. Okay. He's a distinguished professor from Kumamoto University in Japan. He's a research professor in the Institute for Solid State Physics and Optics of Heinrich-Wigner Research Center for Physics. He was in a postdoctoral position in the Studics NEF University of Uppsala, Sweden. He was a research fellow in the Laboratory of Material Science of Delft University of Technology in Netherlands. He was a visitor in the Clarendon Laboratory in the Oxford University, UK, and he was a research student at the Laboratory of the Theoretical Chemistry at Laurent Eubons University of Budapest. And he was a visiting graduate student in the Keble College, University of Oxford. It's a pleasure to introduce to Professor Laszlo Puszlai. Today he will talking about interpreting diffraction data, the structure of molecular liquids. Go ahead, Professor.
Thank you very much, Yvonne. I don't know how to move the screen, so will you? You do it. So what do I do? Do I signal you that? Okay, well, this is very unusual situation for me. Anyway, thank you very much for coming, so many of you today, and also maybe some people in the all over there. Yeah, okay, maybe, yeah. You see, I'm not a very photogenic, I'm afraid. So maybe I should do it like some, I don't know. But anyway, so yeah, that's the title of my talk, and I think I have to apologize in advance because maybe what I'm talking about will not be completely understandable for all of you just because the background of yours is different from mine. But I hope there will be at least one story along the way which may capture your attention. But let's see how it goes. So can we just go one further? So first, I'd like to show you where I am from. Okay, next one, please. So yeah, Budapest, Hungary. I mean, the most interesting thing that you should, but this is another kind of apology that, as you see, over the past 5 years, I had 3 email addresses, 3 domain names even, while I haven't moved a centimeter from my desk. So this is just, I was sitting somewhere, and in the meantime, my email is changed and my domain name changed. So, you know, under this situation, it's not always too easy to concentrate on search. Anyway, can you please, yeah. So these are some pictures. So the one here, 6 years ago, I was in this building, and as you see, there is a chimney behind, and the chimney is there because there's a nuclear reactor behind this building. And in this nuclear reactor, there used to be a neutron diffractometer, which we use happily. But then situation changed, so we moved to another building. This one, this is building number 1 of this whole site. So if you look at this area view here, so this is the chimney. You can probably find it. And this is the building I used to work in, and this is the building I'm working now up here in this one. So this is one pretty nice area, actually. It's a big park, even like it's called the park forest. So that it's not allowed to put any more buildings on this area, only if you demolish one. So there's no things like here you have a building just 10 meters across. No way, no way, it's not allowed. So, okay, so the main focus of this talk, and actually my focus in my scientific career, is the structure of disorder at the atomic level. So our main goal is to understand what's behind, the next one, please. Actually, I can do it somehow. So these are the kind of data measure by diffraction. And if you know about diffraction in general, then you may think of crystallography, because this is what you might, I don't know if you have an X-ray diffractometer in this building, very probably. Okay, so if you have such a big department, then surely X-ray diffraction, X-ray crystallography is the main way of characterizing a structure of a material, or in general a material. These kind of things you can also take by your diffractometer here, although not so easily. So these are the so-called total scattering structure factors that you measure when you want to determine the structure of a disorder system. What is a disorder system? It's, for me, mostly liquids and gases, and there is also disorder in crystals, as we will see in later. So this part is all carbon dioxide. You may not recognize it at once. The nice thing about carbon dioxide is that you can have it in very, very different thermodynamic conditions. So all these here are supercritical states. All these things here are mostly also cost of the liquid phase. So you either cool or press or both. This is something connected to Mexico, actually, because this is a structure factor of activated carbon made from, I think, coconut shells or something like that. And we wanted to know something about the porous structures. I think one of you, you heard this small topic from me. I didn't remember it was here, but it's good. So this is a Mexican sample here. And the most topic today is this. These are molecular liquids of very prototypical type, carbon tetrachloride. In the chemistry lab, you know carbon tetrachloride. These things are a little more dangerous, so you don't want to deal with, for instance, thin tetrachloride, the same way as you do it with carbon tetrachloride, but it's the same family of liquids. And you have two sets. These are neutron diffraction data, and these are X-ray diffraction data. And in some cases, the contrast between these two is really excellent. Can you please? Okay. So for molecular liquids, the main question is, how do molecules turn towards each other? In other words, what is their orientational correlations? The problem is down here. I didn't want to make it very public. There is no direct measurement for that kind of a thing unless you see it. So for instance, if you have large nematic or whatever liquid crystals, then in some cases you can actually have an image, an electron diffraction, image of the thing. But otherwise, no direct measurement. So what do I mean by orientational correlations? This is just a cartoon here. So what we want to know if molecules turn towards each other like one of those ways, and you see even for tetrahedral molecule, you have a lot of possibilities. And the main subject today is this carbon tetrachloride molecule. As you know, it's CCr4, 4 chlorine atoms. And the thing I'd like you to notice is that you don't see the carbon atom. So for the outside world, there is no carbon atom. There are 4 kind of fused chlorine atoms around, and the carbon atom is somewhere in the middle. Now, if you look at the other members of the family, these are the tetrahedral liquids, depending on the size of the center and of course the ligand, then this is, for instance, tin tetrachloride. So the tin atom is pretty big, and the chlorine atoms here, they behave very differently from here. So here you do see the center of the molecules, here you do not. And this is the biggest molecule of all. This is tin tetraiodide. It will have some significance later. You will hear it later. And these are just possible orientations. So we want to have an idea whether they turn towards each other with one corner or any other ways that you can imagine. Let me just go. Well, we take it from textbooks, you know. So this is nothing. You can actually, from the data, you will see, but in the beginning, it's just from textbook. So what is carbon tetrachloride for us, for those who want to understand the structure from diffraction? You have 3 functions, which are called the partial radial distribution functions. This is a concept which I probably should have introduced, but in any case, it will be sort of easy to understand that once you have a 2-component system, carbon and chlorine, then there are functions that describe the relative positions of carbon atoms to carbon atoms to chlorine atoms, and chlorine to chlorine. So this is why we have 3 of these partial radial distribution functions. Problem is, in this particular case, we have at most 2 diffraction measurements. One can be X-ray, and the other one is neutron. And as a sideline, I must tell you that these 2 unfortunately not too different from each other, because in this case, you have a dominance of chlorine, and in this case, you have an even bigger dominance of chlorine. So you don't see visually the center, and you don't see the center by diffraction methods either, because the scattering power of the center, carbon atom, is low compared to the chlorine atoms. But it doesn't matter if you think a little bit about it, because once you know the positions of the 4 chlorine atoms, the position of the carbon atom is unequivocal. So it cannot be anywhere else but in the middle of this tetrahedron. So the general rule is you can determine these functions solely from diffraction experiments if you have as many independent diffraction experiments as many partials you have in the system. Maybe it wasn't very understandable, but in this case, you should have 3 independent diffraction measurements in order to determine these functions, but you only have 2. So you cannot do a standard evaluation of the diffraction data. So as I said, the standard determination is not working, and so what to do? Okay, what we do is we want to make models, and I skipped a lot of thoughts here because I wanted to get somewhere in the end, but what you should try to remember in general, what we need structural models like this one. You know, these are coordinates, and I know that some of you are working with simulations, so you can think this as if it was a simulation result. it actually is a simulation result anyway. So we want structure models like that, three large sets of three-dimensional coordinates, which are consistent with diffraction data. I mean, data that you measure within the uncertainties of the data. So that's the general goal. This is how to deal with situations when you do not have enough measurements, you don't have enough information. And the thing that we should remember here is that there are standard simulation techniques, like you do your proteins, and well, other people do something else. Victor are doing with Mario the methanol and water and stuff. So these standard simulation techniques they are very fine, very good. I love them, really, honestly. The problem is that you have to guess somehow the interactions between atoms of these kind of liquids. And the development over the past 20 years is really enormous. So for many molecular liquids, you can actually find very good classical potentials. For these methanol systems, of course, it's a problem that you have hydrogen bonding, and hydrogen bonding is strictly non-classical. In classical terms, it can only be approximations. So we want these kind of models that will give you back the signal that you measure. Is it possible? Okay, that's the general scheme. So this is called an inverse approach in the jargon. So instead of measuring something, well, you have to measure something, but separately. And instead of imposing an interaction potential on the system, you try to generate models in some way. I will tell you one possible generate, just to have boxes of coordinates. You have to see if the model is good. That is the model can match really the measured diffraction data. And then if not, then you have to try to modify the model so that the agreement in the end with experiment will be perfect, which is of course good and perfect. I should have a philosophy lecture here as well, but anyway. Okay, so this is one possibility. And this is used, in many cases, this is the main topic of a talk of mine, but here I want to get over it very quickly. So this is a method, very simple, called the reverse Monte Carlo method, by which you have a measurement. This is your measurement, this wiggly line. And you have a model, which I generated very simply, just putting particles into a box as it was in a crystal. And what you want is that in the end, the spiky lines, they would match the wiggly line. And there is a very simple algorithm for that. So you basically shake this simulation box in a way that you move one particle at once, just as in a normal Monte Carlo procedure. You investigate whether the new position gives you a better agreement with your experimental data. So obviously, this is a very bad agreement. And this is a little better, also very bad, but a little better. And in the end, you get something which is within the statistical errors of your data. And with 100 particles, I hope you believe me that this is statistical. So I mean, this is all. And it has a lot of closer. Oh God, people don't hear me. Anyway, I get the next one. So that's a very simple procedure. And at the end of this procedure, this is the first published agreement between a model and the measured data. This was on liquid argon, everybody's favorite pet in the liquid state investigations. And the agreement is good, I would say. There is something here, but that is, before you ask me, I tell you that the measurement actually was starting here. So this part was not measured, even though the people in more than 50 years ago, they put this curve into the paper. And I mean, after some investigations, it became clear that this part was approximated because the measurement started here, which is actually normal for liquid diffraction data, around half an inverse angstrom. And then they drew a straight line to this limit here because this can be guessed, this point here, S0. This is something to do with the isothermal compressibility. So diffraction starts here. Here there's no measurement. And this one point is from isothermal compressibility. So that was the main reason for this little discrepancy. So, this is our aim. This is what we want. Yes. Yes. Obviously, it's smoothed and stuff. So, anyway. Can we go further? Now, this is very nice. One component, one measurement. Hooray. We can do everything. Almost. But in most cases, like in the case of carbon tetrachloride, we have this situation. It's, yeah, information deficiency. Why do we have information deficiency? One more time, because if you want to derive the two particle correlation functions in the system, three of them, a carbon-carbon, carbon-chlorine, and chlorine-chlorine, you need to have three independent measurements. What independent means, I can tell you later, but just try to remember this. So in most of the cases that have any relevance to real life, there is some sort of information deficiency. In carbon tetrachloride, it's easy to understand. We don't have enough measurements. Okay, we have to do something with that. Okay, we go further. Now, a little more philosophy here. Okay, this we understand with carbon tetrachloride, but how about in a place where there are a sufficient number of measurements for determining the partial radial distribution functions? And this was a, for me, very famous case. 1992 in the Netherlands, we were dealing with metallic glasses, very interesting systems. This one in particular was a famous one that time, nickel 81, boron 19. And then a very kind and very talented PhD student came to me on one day, and he said, look, these two structures are different. And by nature, impossible, because they had the same GFRs and the same the same angular correlations. And I told this guy, Peter Downer, that look, if you show me a black, which you could measure here in your lab, with black peaks, then I will believe you. In 10 minutes, he came with these two pictures here. In this, and then I said, of course, this is layers here, obviously. And this model was started using reverse Monte Carlo from a layered like crystal structure. This model was started from a random distribution of particles. So is this a problem or is it surprising? It was not a very nice surprise for me, but it should not be surprising because what you measure, this is what you have to remember, by diffraction, apart from crystallography, is two-body correlations only. So you can probably imagine that you have, well, you don't have to imagine, here you go. They have the same partial radial distribution functions. And obviously the difference is there, but not at the level of two-body correlations. These are multi-body correlations. I cannot even guess how many particles you need to describe such kind of layered crystalline arrangement. So is this a problem? Well, it is a problem in a way, but this is what Mother Nature gave us. So, we have to live with this if we want to know anything about the structure of liquids. On an advantage, I know people who said that, oh yeah, very good, because this way, now we have a method by which you can detect and show the the ununiqueness of the data you measure, not the method, the data. This goes to the data, really. Can we have the next one? So what to do in a modeling method like RMC? Well, we have to introduce constants. So because now we know, well, not now, but a long time ago, we knew that there are many, many different possible particle arrangements that will give you the same diffraction signal. You really have to try to constrain the volume of the available configuration space for your system. Now, people with some statistical mechanic background would understand what I'm saying here now. Anyway, you should try to be sensible because you know that not all the configurations, all the particle arrangements will give you sensible results. So we must, yeah, I said that, meaningfully narrow the space of this. So what kind of constraints are in the software that we are using presently? It has its name. So we have neutron diffraction and sorry, this is jargon again, X-ray diffraction, and also something called the anomalous X-ray scattering. This is related to this. It can only be done with a synchrotron, and I'm afraid if you want to do that, you either go to the south, because I know that in Brazil there is a synchrotron at least, or to the north, because in the US also there are some. But in Canada too, by the way, these days, so maybe Canada is better, but okay. We have a lot of constraints on the coordination number, and this actually helps you to introduce the concept of a molecular shape, because the molecular shape is not given by diffraction experiments. It is given in crystallography, but not because of the topology of a molecule. In crystallography, it's given because you have basically an infinite amount of information concerning the crystalline planes that are in the system. And if your software does it for you, and then suddenly something will come up with a sensible molecular structure, but it is not in the diffraction data. Only distances within the molecule. Angular distribution functions we also constrain many times, and in some versions we actually put interatomic potentials into this system just because it is not necessary. But if you have a good idea, a really good idea about the interactions in a system, then it's a good constraint. It will constrain, again, the available volume of the configuration space for you. Yeah, we can go now. So so why do we use this kind of method? This is just structure modeling method, YRMC. First thing is full range of diffraction data can be used. Interatomic potentials can be used, but not necessary. And I think this is the most powerful thing. So you have a system that you are really interested in, like liquid water, which I've been interested in for God knows for how long, and still can do something on it. So different types of data you can put into one single system. So how do you imagine when you have different kinds of data? Very easy. You have one simulation box. You have a range of measurements. For instance, Newton and X-ray diffraction, sometimes EXAFS. This is X-ray absorption spectroscopy, very useful in cases. And then you just try to move the atoms around in that very box that would fulfill this criterion that they have to describe the measured data with its errors for all of these. So in a good case, in the end of a reverse Monte Carlo run, what you have is an arrangement of particles that are consistent with all these data. And this you usually don't get by any other methods. Okay, can we go further? Now, back to carbon tetrachloride. You will see why I needed this little bypass. So, as I said, it's the prototype reader systems, and actually, as I noticed in the literature, it's also basically a prototype of all molecular liquids in many ways, because it's a really three-dimensional construction, not like CS2 or N2 or O2. Can we go further, please? Okay, this you have already seen, just a reminder. 3 partial radial distribution functions, 2 measurements, and then modeling will come. Can we go? And this I also said, but just just everybody remembers. Can we go further? Okay. So what we will do with carbon tetrachloride, or what was done before, there are experiments, as you will see, diffraction in this case mostly. We will make some structure models, and we will check if the structure model is consistent with what you measure. And then you will go to the determination of the orientation correlations from the coordinates. And from this point on, actually, this will be our focus. So we know kind of how to make a model, and now we want to understand the model. That's the next step. Can we go forward? Okay, this you don't have to see even. This is just a list of measurements, diffraction measurements that have been performed on carbon tetrachloride. And if you look at the early ones, I mean, 1932, 1934, lots of in the 40s and 60s. But strangely enough, even later on, yeah, we did a couple of measurements. Yeah, so it's a really wide range of measured data, and a very simple system. I mean, carbon tetrachloride in the organic chemistry lab, you don't even think that it is worth investigating on its own. Can we go a little further? Okay, so here we put many of these data sets on one graph. These are the I don't know if it's FQ, what is that? Okay, so these are the Newton data here on the top of each other. There are differences, but I mean, if you would just average of all of these, then you would get something, reasonable. This is X-rays, of course, they were before the Newton data, and the same can be said. And yeah, there are here and there, but in general, there is not a huge divergence among the data. Can we go further? And of course, there have been computer simulations. Molecular dynamics started in the early 80s. And the thing, I mean, the first cloud on this nice sky, which is full of diffraction data and stuff, was here. There have been molecular dynamics simulations. Of course, in the beginning, very small amount of particles, like 100 molecules or something. Nowadays, 10,000 molecules, not a problem, not even on your laptop sometimes. So that's really not a big deal. The thing is, they have not checked the agreement between their models and the measurement in Q space. That is in the reciprocal space where the data have been determined. And then what is happening, and now this is basically an introduction to the rest of the talk, what was happening is that somebody has an idea and they try to kind of match this idea with what they measure. And it didn't go too well, as you will see in a minute. That was reverse Monte Carlo also, oh God, almost for 30 years. This study was ours, and this was the first time when we showed that previous ideas about the structure of molecular carbon tetrachlorides were not very good. Okay, then we go further. These are just sketches of diffraction data. And you see if the GOFRs, I mean, the total radial distribution functions were considered, it was shown that I mean, simple Lennard-Jones-based potentials basically were kind of working. Can we go further? So what was the problem then? Why the structure of carbon tetrachloride was not fully revealed until, I would say, almost 2010. And the problem is the interpretation. So again, what you had, you measured something, then you had a model from usually molecular dynamics or Monte Carlo simulations, and then these two things lived sort of separately. So the model, the simulation boxes have not been compared with primary experimental data. And this has caused problems. Okay, so what sort of problems? Okay, in the early days, you will not have to read, I will read it. I'm still amazed in some of these things. Okay, 43, 80 years ago, or whatever, a subsidiary peaks about 3.5 and 5 angstroms in the total GFR represent frequently recurring distances between nearest approaching atoms in different molecules. Very important thing to say in 1943. The presence of peaks implies slight preferred orientations. Fully agree. This guy said it in 43 on the basis of probably not very high quality X-ray diffraction data without any computers. So, you know, recording on a photo plate and then whatever you can by hand. So amazing. If famous person L. Nathan in which approaches the packing of chlorine atoms as closely as the geometry of the molecule permits, appears to be the configuration realized in the liquid. And actually, I would not be able to say this better. This was 67, you see. It was a very good track, a very good track. Also, he said, a model for the liquid structure, which may then be tested against diffraction data. Amazing, that is what is needed, tested against diffraction data. And then came the disaster. Now I can say that. The disaster broke out in 1971, and that was the time. Why is Apollo model? You will see it in the next slide, not now, but just, I'm just telling you. In this paper of very, very influential diffraction experts, including Peter Egerstaff, for instance, who has been considered to be the father of diffraction, of liquid diffraction, they said something about a specific alignment. And the paper says, naturally, this is not really a rigid orientation in the liquid and cannot hold for all molecules, since one cannot even make a crystal in this way. However, it is not seriously inconsistent with the known liquid density. So their suggestion was that very plausible, two tetrahedral molecules, they just align like a line. Their axes are aligned. So as sometimes they say it, one of the ligands of one molecule goes into this hollow, as they imagined, made from the 3 chlorine atoms of the other molecules. And I mean, these people who mentioned this first, they were honest and smart. They said it here, that this cannot hold for all pairs. It cannot hold for like really straight. But then, of course, all the people in the literature who started to follow the thoughts of these great people, not well enough to follow, by the way, they started to do things that diverted the whole line of investigations. So for instance, from this rough idea, saying that this is the, the ideal, but all sorts of deviations are possible. 20 years later, there were things which said that it's not like that. I mean, not zero, but rather like one of them is 20 degrees tilted and stuff. And we can go further. I mean, this was disaster. Can you please go? So this was the paper, what they said. And again, this was just a suggestion. And it was very easy to refute. I mean, later we did it. We tried to construct only dimers like that. There were dimers in the system like that, not like everybody has 4 neighbors, as some of the papers said. Then it was impossible to reproduce the experimental data. So Apollo model out, at least should have been, but it didn't happen. Can we go further? So that's Apollo stuff. I'm just looking around. I mean, I don't really remember this. This was the famous Soyuz Apollo joint space venture between the Soviets and the Americans, the US. And I really have no idea, maybe if there is something. So here you go. This is one of the carbon tetrachloride molecules. And here comes the other one with the, yeah. So, Apollo model. And this is a nice name, really a nice name, captivating. Apollo model, fantastic. But it's not true, very simply. It could have been shown that it's not true. It cannot be true. And then, after the 70s, each of 4 neighboring molecules has one of its chlorine atoms, blah, blah, blah. Each. Then, poor Japanese guys. It may be said that carbon tetrachloride molecules have a tendency to keep the most stabilized orientational correlation, namely the head to tail. I mean, head to tail. Strange head, strange tail, but this is what they meant. And so on and so forth. Many, many, many papers. Can we move forward? Yeah. And you see, this whole attitude was really strange because there was already in the 70s, and maybe some of you here are actually doing something like that. And in the beginning, of course, quantum chemistry was not powerful enough. I mean, the computers were not powerful enough to do more than dimers. And if you look at this collection of possible dimers, these people, okay, that was 2005 already. The face-to-face alignment is more favorable than any of the corner-to-face. And this, of course, goes against your imagination. This is face-to-face. Where is the face-to-face? Here you go. For instance, this one. So instead of this, you do this. But the point is, and as L. Nathan said, 67, and then I don't know, he went a little mad probably. I would also, I don't blame him, is that he said that the probable arrangement is the one which can give you the highest packing fraction of chlorine. And it's pretty obvious, seemingly, that if you do this and not that, but you rotate a little bit, and then you have at least as close a contact than as in the other case. So not even quantum chemistry for dimers suggested this kind of arrangements. Can we go further? So, as usual, the breakthrough has occurred not in the terms of simulation. Okay, IMC helped a little, I like to believe it, but in MDs, everything was there. Just the interpretation should have been made better. So, this is what we are using these days for describing orientational correlations. And this guy called Ross and Ray from Barcelona, he had a very clever construction for tetrahedra. He didn't mention in the first paper like carbon tetrachloride or something. This is just general geometrical objects, if you like. And he said that in a clever or appropriate categorization, you only have basically 6 different kind of orientations. And of the 6, one of them is this one, the corner to face one, 1 to 3 as we call. And there is other things. So what is these 1s and 2s? So what you do is you join the 2 centers and you then construct planes perpendicular to this line in both molecules. And you just count later how many atoms from one and the other molecule you have in this space. Is it for me or is it? Yeah, okay. It would be fine actually, because if I started at 2, then it would be 45 minutes. So anyway, so you have 1, 1, which in other words, corner to corner. You have corner to edge, because you say here is 1, here is 2. Corner to face, Apollo, if you like, 1 to 3. Edge to edge, as you will see, this is actually the most probable. Edge to face, also, yeah, quite probable. And that is this famous face to face, which one of the studies, oh yeah, sorry, the quantum chemistry study said that this is what's happening. So what has this guy did? Okay, this is all very fine, but you can do this for each and every molecule in the system. So in this way, you will have a characterization of all the orientations between any 2 molecules in the system. Of course, if the molecules get far away, then there's basically no correlation. Usually, you will see it in a minute. So basically, distance-dependent correlation functions can be constructed on the basis of this, I think, really simple imagination or construction. Let's see what they look like. Can we go further? Okay, so that's orientational correlations in carbon tetrachloride as we think of it now. So we apply this construction, which I just showed you, and then we draw these functions as a function of distance. So this is how far our, in this case, reverse Monte Carlo configurations went. And then you can see, first, we just see this one. So this is the so-called real system. And it's obvious that at short distances, you have really a dominance of 3 to 3. That is face to face. Just as quantum chemistry said, by the way. A little further away, you have 2 to 3. That is, anyway. So you can imagine. Ah. Well, I don't know how to, but this is very smart. But I'm not smart enough. So anyway, so these are, you see, these numbers do mean something here. These are actually ratios. The sum of these numbers, okay, the asymptotic limits should be 1, because this is just, you know, the ratio of a given orientation at a given distance. Yeah, maybe it's a little complicated, but you know, I lived in this world for a few years, so for me it's probably a little easier. Oh, good, I do something here. Anyway, so these are the ones which are the most frequent. And do you see anything like 1, 2, 3 among these? No, only here, down here. And do you see, this is more than 20% at the asymptotic limit. 1 to 3 in the asymptotic limit is something like 6%. And it doesn't go up very much. So this orientation in this tetrahedral liquid is not really significant. So anyway, this is, you know, a box. We like to draw things. And this is 2, 3 here, exactly. Just in order to show you. So this is a kind of a section of our configuration. And you can see that this is an edge here, 2 chlorine atoms from the same molecule. And this is a face of a tetrahedron. So this is actually very interesting for us. These are half spheres. So if you have no experimental data, no potential, just the geometry of the molecule and the topology, and you play this game like a half sphere Monte Carlo, then this is what you get. And I think here the difference is really striking. So it's pretty obvious that in a half sphere system that is without data, without interactions, apart from this repulsion from the half spheres, there is basically no correlation beyond like 10 angstroms. Whereas this is what the data brought in. And I was so happy that finally a place, I mean, I've been playing with quite a large number of diffraction data over my life. And here, the information content of the diffraction data, again, a little bit of philosophy, is huge compared to what just this pure geometry would give you. So hooray, hooray. So this is how we understand it today. Can we go a little further? And then we considered all sorts of tetrahedral liquids. Oh, yeah, thank you. Good, because then those lines would stay forever. Okay, so then in the end, it was very pleasing that after like nearly 20 years of dealing with tetrahedral molecules with students like Silvio and the other Laszlo, where are these names? Yeah, Silvio Pototsky and Laszlo Leitner, previously PhD students of mine, now members of our group on a permanent position. So we were able to compare, to suggest a review in chemical reviews about about these tetrahedral liquids. That was the title of it, structure of neat liquids consisting perfect and nearly tetrahedral molecules. So, I mean, I think it's very nice. It gave us such a, at least to me, such a, almost like joy, especially when we could finish it finally. Well, that was it. But you see, it wasn't very nice because it has been viewed, I checked it this morning, it has been viewed 1,500 and whatever times, and the number of citation is 25. So it's not a very good, ratio of, work put in and then the reward, so to speak. But you see, the thing is really, I think now this case is closed. So we understand these tetrahedral liquids. Okay, so what do we know? A little, maybe a few examples. Can we go further? So we basically, if we really want to make this thing simple, we wanted to understand the influence of varying atomic sizes and the influence of distorting this TD symmetry. And it's, these are all very well known to a chemist because we started from carbon tetrachloride. We replaced one chlorine atom by hydrogen, chloroform, very nice material, especially for, spies and stuff. And then methylene chloride, still a liquid, just about, still a liquid at room temperature. If you take one more chlorine off, then it will stay a gas, like very much down the temperature. So these are all liquids. So we were able to investigate how these orientational correlations, the thing was that they deteriorate. That's the whole point. We didn't know it, but this is how it came up. And the other thing, I showed you these examples, and this is why I showed you at the beginning. So that's carbon tetrachloride, center is not visible. This is tin tetrachloride. Only the center is visible by X-rays because tin has 55, 54, I don't remember, electrons, whereas the chlorines don't have that much. And this huge molecule, tin tetraiodide, which I will tell you in a minute why it's so important. It's actually not a liquid. You have to melt it. But it goes into a nice liquid, so it's fine. Right. So what happens when you change the size ratios? So carbon tetrachloride, you have very, very, very long range oscillations. Actually, these oscillations of the orientation and correlation functions, it went on at the end of our simulation box. So it's really long range things. If you go to this other thing where you have a much bigger center, tin tetrachloride, then this oscillation died, well, something like around 20 angstroms. And when we go to the tetraiodide of tin, then you see that the intensities of these functions they lower, and also the noise is much bigger. It means it's just not so expressed. And can we go one further, please? And this is why we need tin tetraiodide. After reading this Apollo literature, or how to put it, is 50, or I don't know how many papers saying that it is obvious from the data and from the simulations and God-given, whatever, that it must be Apollo type models in carbon tetrachloride. The answer was no. But there is one place, finally, SNI4, where there is a small distance range when the Apollo type arrangements are really dominated. So there is only one of all these tetrahedral liquids that we have investigated where this 1 to 3 correlation is realized. So yeah, we were happy finally. Apollo, all right, but not for the carbon tetrachloride. Anyway, can we go further, please? Okay, so what happens when you make the geometry more distorted? I don't know what happened here. Anyway, this is chloroform here. That is methyl chloride, and you see again in the center very long range correlations between the orientations of molecules. Whereas in both of the other cases, when you basically break the TD symmetry, then you get much shorter range correlations. So intensities and ranges of oscillations decrease with distorting the perfect tetrahedral geometry, just as it happens when you actually basically you increase the size of your tetrahedra. So it seems like CCl4 molecules are so compact, so nice, that an orientation of one of them will already say something about the orientation of its neighbors, and it's propagating for very, very long distances. That is, orientational correlations in liquid carbon tetrachloride are huge, whereas in other tetrahedral liquids are not so huge. Okay, I'm sorry, I need 3 more transparencies if I'm allowed. So this is basically the end of one sector. But this I wanted to show you because I had this idea that you may have an X-ray diffractometer in this building, and you may see diffraction patterns that are dominated by black peaks. This is what you want. When you have a crystal, you want to know the crystalline structure, and it's fair enough. Of course, it would be better to have a single crystal diffractometer, which you might also have here because of the proteins or whatever. Okay, so now what we do is we try to understand power diffraction data of various phases, including crystalline phases, of another tetrahedral system. So this is the link. Can we go further, please? So why? I mean, what a contorted idea to use structure modeling for a crystal. I mean, from a crystal, we know everything, don't we? Well, can we go further, please? So that's what you expect. A good crystal and a very neat black pattern. Does this happen always? Can we go get the next one? The answer is clearly no. So these are 3 phases of carbon tetrabromide. Carbon tetrabromide has a ordered but monoclinic crystalline phase at room temperature. If you go up to about 50 degrees Celsius, then you get a crystalline phase, which is very nice. It's cubic, but it's disordered. I will show you what that means. And at whatever 100 and some Kelvin degrees Celsius, it will just melt, and then it behaves like a nice tetrahedral liquid. Okay, so these are the G of R's here. Again, ordered room temperature and plastic phase. And here, if you notice, then these are black peaks. I mean, I don't want to, but these are not. And actually, if you calculate the intensity underneath the curve that you measure, it turns out that 90% of the scattering that you measure from, especially from this disordered crystalline phase of carbon tetrabromide, is not from black peaks. So in a normal kind of evaluation of diffraction data, what they do, all these RETWELD programs, what they do is that they treat it as background. But I would say 90% background, and what do we do with the rest? And this is not a general case. This is disordered crystals, but this is not the only one, actually. So can we just go on further? And you see, again, that this is the measured data for the 3 phases. And it's obvious that the most black peaks you find in the ordered phase, you find just I mean, this is cubic, so of course you don't have many black peaks here. But this kind of diffuse part, they are very similar to the liquid part. And how to, I mean, understand this? So these are the partial G of R's here. And what you should notice that the level of disorder at the BR correlations is about almost like the same for all the phases. And how to visualize that? Can we go have the next one? So this is the asymmetric unit of the ordered phase. So this is how, I mean, smeared out when you use structure modeling by reverse Monte Carlo. But when you go to the disordered crystalline phase, you still see these black blobs here and there, which are the carbon atoms. But as you see, the position of the bromine atoms are completely, well, not quite completely, but they are random. So this is the liquid part, if you like, of the disordered crystalline phase of carbon tetrabromide, whereas this is the crystalline part. So these blobs here, the carbon atom positions, they are responsible for the black peaks. And these things here, they are responsible for the diffuse scattering. So can we go further? Okay, now I'm really finishing. And I'd like you not to forget that the effective route to the atomic structure of disordered systems, including molecular liquids, is you try some sort of an inverse approach and generate the material and then you try to see if the measured signal is the same as you calculated or vice versa. And when you have this consistency, then you try to analyze the model. This, I really thank you very much for coming today, and hope to see you sometime in the future.
Please, don't be shy. One question, please.
Oh, I give you this.
Do you know recently people from quantum chemistry has tried to tackle this problem to describe correctly the interaction between these molecules? For
Between
diamond?
carbon tetrachlorides. These systems really, I mean, after this review, nobody is interested. No, there are some, I mean, because we've been studying these for a very long time. I know that there are some individual systems. One is actually germanium tetraiodide. It's interesting because the center is a little bigger and the iodine is big. So maybe it's another Apollo, but actually these days when you have to do whatever innovation, at least in our country, anyway, then nobody is really interested in, at least from the people who are giving or not giving us money. So no, they are not doing this. They are doing something more useful, as everybody thinks. It's the end of the story, I'm afraid.
Other questions, please? I have a question. So we are interested in how the wall affects the behavior of the fluid, particularly in the case of the absorption, okay? So, for example, in the case of water, we focus in the surface phenomena like layering transition or water anomalies or everything, you know. So are there studies using reverse Monte Carlo methodology in order to investigate this kind of phenomena or something related with that? So,
but the short answer is yes.
okay.
Longer answer, look, I give you a paper of ours, which I was not very deeply involved in. This paper was basically from a collaboration with people from Madrid, not from the same university as Carlos, but there is this research institute, which is not a university, which I cannot remember now. So people made some sort of a porous material, nanoporous in this case, and they put, I think argon was one possibility. Yes, because there are two isotopes of argon, so neutron diffraction was very good. And the other one was, I don't remember. I mean, I will give you this paper. And the good thing was that you could kind of guess the absorption isotherms when measuring different stages. But this, I mean, you have the material, the porous material, which is crystalline in most of the cases, at least what they did. And then you have this something which you put in the pores, and that is not crystalline anymore. So what I wanted to say is that this is very complicated. The results took quite a long time to get, and I don't remember if we had anything really new. We had the general ideas kind of confirmed, but no new phenomena at this level. And as far as I know, there has not been any continuation of these studies because, you know, argon, you buy the argon isotope for neutron diffraction, that's a lot of money. You lose it basically at the whole that you buy, I mean, at least what went in. So again, however interesting it would sound, it is just, you know, cost over benefit. So the cost here was bigger than the benefit, I'm afraid. It was a nice Journal of Physical Chemistry C paper, accepted basically immediately, cited by 5 over the pi. So, you know, I don't think it's going on any further. So.
Other questions? No more questions? No? Okay, so thank you again, Professor Putzai, for the excellent presentation. So. We have a small gift for you. This is a mug for of the department. Yeah. This is a mug of the chemical department. This is for you. Thank you for the.
I don't know what to do.
Thank you for the presentation. Okay. The microphone. Okay, so I'm going to switch to Spanish in order to read the constancia. Okay? Says, el Departamento de Química de la UAM Iztapalapa otorga la presente constancia al doctor Laszlo Putzay por impartir dentro del ciclo de seminarios del Departamento de Química del trimestre 25I la conferencia Interpreting Diffraction Data, the Structure of Molecular Liquids, el día 26 de febrero de 2025. Firma el doctor Jorge Garza Holguín, jefe del departamento, y el presente doctor Víctor Manuel Trejos, coordinador del seminario. Mil gracias por la presentación y Casa Abierta al Tiempo, Ciudad de México, octubre 2025. Y muchas gracias a todos por los que asistieron al seminario. No sé si quiere el doc dar unas palabras. Entonces agradecemos a todos la presencia y los invitamos nuevamente a nuestro próximo seminario que será anunciado en las redes sociales. Mil gracias.